Introduction. The universe is a vast and intricate tapestry of cosmic structures, ranging from the tiniest particles to the largest galaxy clusters. Understanding these structures is fundamental to our grasp of the universe's formation, evolution, and ultimate fate. At the heart of this exploration lies the concept of gravitational anomalies, phenomena that deviate from our expectations based on established laws of physics. These anomalies not only challenge our understanding, but also provide critical insights into the unseen forces shaping the cosmos. Overview of cosmic structures. Cosmic structures can be categorized into several hierarchical levels. At the smallest scale, we find galaxies, the fundamental building blocks of the universe. Each galaxy hosts billions of stars, along with gas, dust, and dark matter. The Milky Way, for instance, is a spiral galaxy that contains an estimated 100 billion stars and is part of a larger group known as the Local Group, which includes Andromaly. Beyond individual galaxies lie galaxy clusters, which are collections of galaxies bound together by gravity. These clusters can contain hundreds to thousands of galaxies and are often surrounded by hot gas and dark matter. The largest known structures in the universe are superclusters, vast groupings of galaxy clusters that can stretch over hundreds of millions of light years. The Laniakea supercluster, which includes our own Milky Way, is one such example, emphasizing the interconnected nature of cosmic structures. At an even grander scale, the universe is organized into a cosmic web, an intricate network of voids, filaments, and clusters. This web is shaped by the gravitational influence of dark matter, an enigmatic substance that constitutes about 27% of the universe. Dark matter's gravitational pull affects the motion of galaxies and clusters, guiding their formation and distribution across the cosmos. Importance of gravitational anomalies. Gravitational anomalies play a pivotal role in our understanding of the universe. These anomalies often manifest as unexpected variations in the motion of galaxies and galaxy clusters, suggesting the presence of unseen mass. One of the most significant gravitational anomalies is the Great Attractor, a region in the intergalactic space that exerts a tremendous gravitational pull on nearby galaxies, drawing them toward it. The existence of such anomalies challenges our conventional understanding of gravity and matter. According to Isaac Newton and Albert Einstein, gravity should behave in predictable ways based on the mass of objects. However, observations at cosmic scales often reveal discrepancies that cannot be explained solely by visible matter. This has led scientists to explore the existence of dark matter and dark energy, which together account for approximately 95% of the universe's total mass energy content. Gravitational anomalies also drive scientific inquiry and technological advancements. As astronomers seek to understand these phenomena, they develop new observational techniques and instruments, such as advanced telescopes and computer simulations. These innovations not only enhance our understanding of the cosmos, but also push the boundaries of science, leading to discoveries that can transform our comprehension of fundamental physics. Moreover, studying gravitational anomalies provides insights into the universe's large-scale structure and dynamics. By analyzing the motion of galaxies and clusters in relation to these anomalies, researchers can infer the distribution of dark matter and the effects of gravitational lensing, where light from distant objects is bent around massive bodies. This has profound implications for our understanding of the universe's expansion and the nature of gravity itself. In summary, the cosmic structures that populate our universe are not merely static entities. They are dynamic and interconnected, shaped by the unseen forces of gravity. Gravitational anomalies, such as the Great Attractor, challenge our understanding of these forces and the fundamental nature of the universe. As we delve deeper into the cosmos, These anomalies will continue to offer invaluable insights, guiding us toward a more comprehensive understanding of the universe's intricate design and the laws that govern it. What is the Great Attractor? The Great Attractor is one of the most intriguing phenomena in modern cosmology, representing a massive gravitational anomaly that draws galaxies toward it. This mysterious region highlights the complexities of our universe and challenges astronomers to rethink their understanding of cosmic structures and the forces that govern them. In this section, we will delve into the definition and discovery of the Great Attractor, as well as its precise location in the universe. Definition and discovery. The Great Attractor is defined as a gravitational anomaly located in the direction of the Centaurus and Hydra constellations, approximately 150 to 250 million light-years from Earth. It is not a single object, but rather a vast region of space, exhibiting a higher-than-expected density of mass. This mass exerts a gravitational pull that influences the motion of galaxies over a significant volume of the universe, attracting them toward it. The concept of the Great Attractor emerged from observations made in the late 20th century, particularly during the 1970s and 1980s. Astronomers noticed that galaxies in our vicinity were not moving uniformly. Instead, they exhibited peculiar velocities that could not be accounted for by the known distribution of matter. This prompted scientists to investigate the forces acting on these galaxies. The first hints of the Great Attractor came from redshift surveys, which measure the light emitted by galaxies to determine their distance and movement relative to Earth. These surveys revealed that a substantial number of galaxies, including those in the local group and beyond, were moving toward a specific region of the sky. This behavior suggested the influence of an unseen mass, prompting astronomers to explore the nature of this gravitational pull. The term Great Attractor was popularized through the work of researchers such as Margaret Geller and John Huchra in their landmark study of the large-scale structure of the universe. Their findings indicated that the motion of galaxies in the nearby universe was not random. Rather, they were collectively moving toward a gravitational center that they dubbed the Great Attractor. This discovery was a pivotal moment in cosmology, revealing the dynamic and interconnected nature of cosmic structures. Location in the universe. The Great Attractor is situated within a vast region known as the Zone of Avoidance, which is obscured by the Milky Way's own galactic plane. This zone contains significant amounts of interstellar dust and gas, making it challenging to observe distant objects through optical telescopes. As a result, much of the research on the Great Attractor has relied on infrared and radio observations, which can penetrate the dust more effectively. Astronomers have identified the Great Attractor's location at the coordinates of approximately 12 hours right ascension and -30 degrees declination. It lies in the direction of the Centaurus cluster, one of the nearest rich clusters of galaxies. This cluster is part of the larger Laniakea supercluster, which includes our own Milky Way galaxy. The gravitational influence of the Great Attractor extends over a region that includes several galaxy clusters, notably the Norma cluster, which is situated near the center of this anomaly. The Great Attractor's pull affects the motion of thousands of galaxies, causing them to accelerate toward this mysterious gravitational center. As a result, the Great Attractor plays a crucial role in shaping the distribution of galaxies in our local cosmic neighborhood. Despite its significance, the Great Attractor remains partially shrouded in mystery. The exact nature and composition of the mass responsible for this gravitational anomaly are still subjects of ongoing research. Some theories suggest that it may comprise a large concentration of dark matter, while others propose the presence of a supercluster of galaxies contributing to the gravitational pull. In conclusion, the Great Attractor is a fascinating gravitational anomaly that challenges our understanding of the cosmos. Its discovery marked a significant milestone in the field of cosmology, revealing the complex interplay of forces that govern the motion of galaxies. As astronomers continue to investigate its location and nature, the Great Attractor remains a key focus for understanding the large-scale structure of the universe and the forces that shape it. The pursuit of knowledge about this enigmatic region not only enhances our grasp of cosmic dynamics, but also holds the promise of uncovering deeper insights into the fundamental nature of gravity and the unseen components of the universe. Historical context. The story of the Great Attractor is woven into the broader narrative of our understanding of the universe. Its discovery and the concept's evolution reflect the significant advancements in observational astronomy and theoretical physics over the last century. This section will explore early observations of galaxy movements that laid the groundwork for identifying the Great Attractor and the development of the concept itself. Early observations of galaxy movements. The journey toward understanding galactic movements began in the early 20th century. In 1929, Edwin Hubble made a groundbreaking discovery. The universe is expanding. By observing the redshift of light from distant galaxies, Hubble formulated Hubble's law, which states that the farther away a galaxy is, the faster it appears to be moving away from us. This observation revolutionized our understanding of the cosmos and provided a framework for studying the dynamics of galaxies. However, even as Hubble's work established the expansion of the universe, astronomers began to notice peculiar movements within our local group of galaxies. In the 1940s and 1950s, astronomers such as Fritz Zwicky and Vera Rubin conducted studies on galaxy clusters and their dynamics. Zwicky introduced the concept of dark matter to explain the unexpected velocities of galaxies within clusters, suggesting that visible matter alone could not account for the gravitational binding of galaxies in clusters like the Coma cluster. Rubin's work in the 1970s further advanced this understanding. She measured the rotation curves of spiral galaxies and found that the outer regions of galaxies were rotating at unexpectedly high speeds. This discrepancy indicated that there must be additional unseen mass influencing the motion of these galaxies. Rubin's findings provided strong evidence for the existence of dark matter, a concept that would later be essential in explaining the gravitational anomalies observed in structures like the Great Attractor. As astronomers continued to refine their techniques, large-scale redshift surveys were conducted throughout the 1970s and 1980s. These surveys revealed that galaxies were not distributed uniformly across the universe. Rather, they formed a complex web of structures. Researchers began to observe that many galaxies were moving towards specific regions of space, rather than receding uniformly as predicted by Hubble's law. Development of the concept of the Great Attractor. The term Great Attractor emerged from these observations when astronomers noticed that a significant number of galaxies were exhibiting peculiar velocities directed toward a particular region in the sky. In 1986, astronomers Margaret Geller and John Hutra published their findings on the large-scale structure of the universe, highlighting a gravitational center that influenced the motions of nearby galaxies. Their work marked the formal introduction of the concept of the Great Attractor. Geller and Hutra's research revealed that galaxies in the vicinity of the Great Attractor were collectively moving toward this gravitational anomaly, suggesting the presence of a substantial mass that was not directly observable. They utilized data from the redshift surveys to map the distribution of galaxies and identify regions of high density. Their analysis indicated that the Great Attractor was located in the direction of the Centaurus and Hydra constellations, within a region known as the Zone of Avoidance, which is obscured by the Milky Way's galactic plane. In the years that followed, astronomers continue to investigate the nature of the Great Attractor. Studies using different wavelengths of light, including infrared and radio observations, allowed researchers to peer through the dust and gas that obscured the zone of avoidance. These observations confirmed the existence of the Great Attractor and led to the identification of associated galaxy clusters, such as the Norma cluster, which is situated near the center of this gravitational anomaly. Despite the progress made, the exact composition of the Great Attractor remained elusive. The prevailing hypothesis suggested that a significant portion of the mass responsible for the anomaly was dark matter, which had become a critical component of cosmological models. This dark matter was thought to be concentrated in the Great Attractor, influencing the motion of galaxies over vast distances. The discovery of the Great Attractor not only advanced our understanding of galactic dynamics, but also spurred further research into the large-scale structure of the universe. It opened new avenues for investigating the effects of dark matter and the role of gravitational forces in shaping cosmic evolution. Subsequent studies revealed that the Great Attractor is part of an even larger structure known as the Laniakea supercluster, which encompasses our Milky Way and provides a broader context for understanding cosmic dynamics. In summary, the historical context of the Great Attractor is rooted in early observations of galaxy movements and the gradual development of the concept itself. From Edwin Hubble's pioneering work on the expansion of the universe to the identification of gravitational anomalies by Geller and Huchra, the story reflects a progression of scientific inquiry and discovery. The Great Attractor serves as a compelling reminder of the complexities of the universe and the ongoing quest to understand the forces that govern it. As research continues, this gravitational anomaly remains a focal point for astronomers seeking to unravel the mysteries of dark matter and the large-scale structure of the cosmos. The science behind the Great Attractor. The Great Attractor stands as a monumental testament to the complexities of gravitational forces in the universe. This gravitational anomaly not only captivates astronomers, but also provides a fascinating lens through which we can explore the dynamics of galaxies and the unseen forces at play. In this section, we will delve into the gravitational forces and their effects, as well as how the Great Attractor influences nearby galaxies. Gravitational forces and their effects. Gravitation, one of the four fundamental forces of nature, governs the interactions between masses. According to Isaac Newton's law of universal gravitation, every mass attracts every other mass in the universe with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. This principle is foundational to our understanding of celestial mechanics and the behavior of cosmic structures. In the context of the Great Attractor, the gravitational forces at play are particularly significant. The Great Attractor is believed to contain a large concentration of mass, including both visible and dark matter, which generates a substantial gravitational pull. This pull affects not only galaxies within its immediate vicinity, but also those that lie further afield, influencing their trajectories and velocities. Dark matter, an elusive and unseen component that makes up approximately 27% of the universe, plays a crucial role in the gravitational dynamics surrounding the Great Attractor. While it does not emit, absorb, or reflect light, its presence is inferred from its gravitational effects on visible matter. The Great Attractor's mass is thought to be composed largely of dark matter, which contributes to the anomalous gravitational forces observed in this region. The effects of these gravitational forces extend beyond mere attraction. They can also lead to phenomena such as gravitational lensing, where light from distant objects is bent around massive bodies, creating distorted or amplified images. This effect provides valuable insights into the distribution of mass in the universe and has been instrumental in mapping dark matter. As galaxies move through the gravitational influence of the Great Attractor, their velocities can change dramatically. Some galaxies may accelerate toward the anomaly, while others might experience deceleration as they approach the gravitational well created by the concentration of mass. These interactions can result in complex motion patterns, leading to a rich tapestry of galaxy dynamics. How the Great Attractor influences nearby galaxies. The Great Attractor's influence extends to a wide array of nearby galaxies, affecting their motion and distribution in significant ways. As galaxies within the vicinity are drawn toward this gravitational anomaly, they experience a collective motion that reveals the interconnectedness of cosmic structures. Galaxies such as those in the Centaurus and Hydra clusters are directly impacted by the gravitational pull of the Great Attractor. Observations have shown that these galaxies are not only moving toward the Great Attractor, but are also exhibiting peculiar velocities that deviate from what would be expected in a uniform, expanding universe. This behavior is a clear indication of the gravitational forces at work. One of the most fascinating aspects of this influence is the potential for galaxy interactions and mergers. As galaxies are drawn closer to one another due to the gravitational pull of the Great Attractor, they may begin to interact gravitationally, leading to tidal forces that can distort their shapes. Over time, these interactions can result in galaxy mergers, which are significant events in the evolution of galaxies. Such mergers can trigger new star formation and lead to the creation of new galactic structures. In addition to influencing the motion of individual galaxies, the Great Attractor shapes the larger scale structure of the universe. Its gravitational pull contributes to the formation of galaxy clusters and superclusters, acting as a gravitational anchor that influences the distribution of matter in the surrounding region. The gravitational forces exerted by the Great Attractor can help determine the location of galaxy clusters, influencing the vast cosmic web that connects galaxies across the universe. The dynamics of the Great Attractor also raise intriguing questions about the nature of dark matter. As researchers study the motions of galaxies in relation to the Great Attractor, they gather important data that can inform models of dark matter distribution. Understanding how dark matter interacts with visible matter in this context is essential for developing a comprehensive view of cosmic evolution. Moreover, the Great Attractor serves as a natural laboratory for testing theories related to gravity and cosmic dynamics. By observing the gravitational interactions in this region, astronomers can refine their models of gravity and explore the implications of alternative theories, such as modified gravity or theories involving extra dimensions. In summary, the science behind the Great Attractor encompasses the fundamental principles of gravitational forces and their profound effects on nearby galaxies. The gravitational pull exerted by this anomaly shapes the motion of galaxies, influences their interactions, and contributes to the larger scale structure of the universe. As astronomers continue to explore the complexities of the Great Attractor, they unlock new insights into the nature of gravity, dark matter, and the intricate web of cosmic structures. The ongoing research in this area not only deepens our understanding of the universe, but also highlights the dynamic and interconnected nature of the cosmos we inhabit. Observational evidence. The Great Attractor, a gravitational anomaly drawing galaxies toward it, has captivated astronomers since its discovery. Understanding this cosmic phenomenon relies heavily on observational evidence, which has evolved significantly over the years. Various techniques and sophisticated instruments have been employed to study the Great Attractor, leading to key findings that deepen our understanding of this enigmatic region. This section will explore the techniques used to study the Great Attractor and highlight significant findings from various telescopes and missions. Techniques used to study the Great Attractor. Studying the Great Attractor presents unique challenges due to its location in the zone of avoidance, an area of the sky obscured by the Milky Way's galactic plane. This obscuration makes observing distant galaxies and clusters in this region difficult, requiring innovative techniques and advanced technology. 1. Redshift surveys. One of the primary methods for studying the Great Attractor has been through redshift surveys. These surveys measure the redshift of light from galaxies, which indicates their distance and motion relative to Earth. By analyzing the spectral lines of light emitted by galaxies, astronomers can determine how fast these galaxies are moving away from us, or in the case of the Great Attractor, how fast they are moving toward it. The two significant redshift surveys that have contributed to our understanding of the Great Attractor are the Southern Sky Redshift Survey, SSRS, and the 2DF Galaxy Redshift Survey, 2DF-GRS. These surveys mapped the positions and velocities of thousands of galaxies, revealing patterns of movement that pointed to the gravitational influence of the Great Attractor. Infrared observations. To penetrate the dust and gas that obscure the zone of avoidance, astronomers have utilized infrared observations. Infrared wavelengths can pass through interstellar dust more effectively than optical light, allowing researchers to observe galaxies that would otherwise remain hidden. The Infrared Astronomical Satellite, IRIS, and the Wide Field Infrared Survey Explorer, WISE, are pivotal missions that have provided valuable data. These missions have mapped the distribution of galaxies and detected warm dust emissions, enabling scientists to identify structures associated with the Great Attractor. Radio observations. Radio astronomy has also played a vital role in studying the Great Attractor. Radio telescopes can detect emissions from neutral hydrogen, HI, in galaxies, providing insights into their mass and dynamics. Notable facilities like the Australia Telescope Compact Array, ATCA, and the Very Large Array, VLA, have been instrumental in mapping the distribution of neutral hydrogen in galaxies near the Great Attractor. 4. Gravitational lensing studies. Gravitational lensing, a phenomenon where light from distant objects is bent around massive bodies, has provided crucial information about the mass distribution within the Great Attractor. By studying how light from background galaxies is distorted by the gravitational field of the Great Attractor, astronomers can infer the presence and distribution of dark matter in this region. Key findings from various telescopes and missions. The application of these techniques has yielded several key findings regarding the Great Attractor, enhancing our understanding of its structure and influence on nearby galaxies. Confirmation of the Great Attractor's existence. The initial redshift surveys confirmed the existence of the Great Attractor as a significant gravitational center. The SSRS and subsequent surveys demonstrated that galaxies in our local group were not merely receding uniformly, but were moving toward a specific region in the Centaurus and Hydra constellations. This collective motion highlighted the presence of a gravitational anomaly that could not be explained by visible matter alone. Mapping of galaxy clusters. Infrared and radio observations have revealed the presence of several galaxy clusters associated with the Great Attractor, including the Norma cluster. These clusters serve as markers of the gravitational influence of the Great Attractor, helping to delineate its extent and impact on the surrounding galaxies. The identification of these clusters has been critical in understanding the dynamics of the region. Insights into dark matter. Observations of gravitational lensing have provided insights into the distribution of dark matter within the Great Attractor. Studies indicate that a significant portion of the mass attributed to the Great Attractor is composed of dark matter, which plays a crucial role in the gravitational dynamics observed in this region. This understanding is vital for constructing accurate models of cosmic structure and evolution. Discovery of peculiar velocities. Further analysis of galaxy motions has revealed peculiar velocity patterns among galaxies near the Great Attractor. Some galaxies exhibit significantly higher velocities than would be expected in a uniformly expanding universe. This observation provides compelling evidence of the gravitational influence exerted by the Great Attractor and underscores the interconnectedness of cosmic structures. The Great Attractor as part of Laniakea's supercluster. Recent studies have placed the Great Attractor within the context of the larger Laniakea supercluster, a vast structure that contains our Milky Way. This discovery has profound implications for understanding the large-scale structure of the universe, revealing how gravitational forces shape the distribution of galaxies over immense distances. In conclusion, observational evidence plays a critical role in our understanding of the Great Attractor. Through the application of various techniques, redshift surveys, infrared and radio observations, and gravitational lensing studies, astronomers have confirmed its existence, mapped surrounding galaxy clusters, and gained insights into the nature of dark matter. The findings from these observational efforts not only enhance our knowledge of the Great Attractor, but also contribute to a deeper comprehension of the intricate web of cosmic structures and the fundamental forces that govern their dynamics. As technology advances and new observational techniques emerge, future research will undoubtedly yield further revelations about this captivating gravitational anomaly and its role in the universe. The Great Attractor's role in the cosmic web. The Great Attractor is not just an isolated gravitational anomaly. It plays a pivotal role in the cosmic web that constitutes the large-scale structure of the universe. This web is a vast network of galaxies, clusters, and superclusters, interconnected through gravity and dark matter. Understanding the Great Attractor's role within this cosmic framework reveals how it influences the distribution of galaxies and their interactions across immense distances. In this section, we will explore the Great Attractor's relationship with other large-scale structures and its impact on galaxy clusters and superclusters. Relationship with other large-scale structures. The universe is organized into a complex tapestry of structures, often referred to as the cosmic web. This web consists of filaments, sheets, and voids, with galaxies and clusters concentrated along the filaments, while vast empty regions, or voids, separate them. The Great Attractor is situated within this web and is intricately connected to other large-scale structures. 1. The Laniakea supercluster. One of the most significant discoveries in recent years is the identification of the Great Attractor as a key component of the Laniakea supercluster. Laniakea is a vast supercluster that includes our Milky Way galaxy and encompasses a large number of neighboring galaxies and clusters. The Great Attractor acts as a gravitational anchor within this supercluster, influencing the motion of galaxies that reside in its vicinity. The Laniakea supercluster itself is vast, stretching over 520 million light-years and containing approximately 100,000 galaxies. The gravitational pull of the Great Attractor helps to shape the distribution of these galaxies, guiding their formation and movement. It is a prime example of how local gravitational influences can impact larger structures, demonstrating the interconnected nature of the universe. 2. Filaments and cosmic voids. The Great Attractor is situated at the intersection of several cosmic filaments, the dense, thread-like structures that form the backbone of the cosmic web. These filaments connect galaxy clusters and superclusters, facilitating the flow of matter and energy throughout the universe. The gravitational influence of the Great Attractor extends along these filaments, affecting the distribution of galaxies and clusters that lie along their paths. Conversely, regions of lower density, known as cosmic voids, are also influenced by the Great Attractor. The gravitational pull of massive structures like the Great Attractor prevents galaxies from being evenly distributed, leading to the formation of these vast empty spaces. The interplay between the Great Attractor and these voids highlights the dynamic nature of cosmic structure formation. Impact on galaxy clusters and superclusters. The gravitational influence of the Great Attractor extends to nearby galaxy clusters and superclusters, shaping their dynamics and evolution in profound ways. Number 1. Acceleration of galaxy clusters. Galaxies within clusters near the Great Attractor experience accelerated motion toward this gravitational center. This acceleration is a result of the gravitational pull exerted by the Great Attractor and the mass concentrated in the surrounding clusters. As galaxies are drawn toward the Great Attractor, they may exhibit peculiar velocity patterns, deviating from the expected uniform motion of an expanding universe. This acceleration affects the dynamics of galaxy clusters, potentially leading to interactions and mergers among the constituent galaxies. As galaxies collide and merge, they can trigger bursts of star formation and influence the overall morphology of the cluster. The Great Attractor thus plays a critical role in the evolutionary processes of the galaxies within its influence. 2. Formation of galaxy clusters. The gravitational pull of the Great Attractor contributes to the formation of galaxy clusters in its vicinity. As matter is drawn toward the Great Attractor, it accumulates along the filaments of the cosmic web, leading to the formation of clusters through gravitational collapse. This process highlights the interconnectedness of cosmic structures, as the Great Attractor not only influences existing clusters, but also plays a role in the creation of new ones. Galaxy clusters that form under the influence of the Great Attractor are often rich in galaxies and dark matter. The presence of dark matter in these clusters is essential for maintaining their gravitational stability. As researchers study these clusters, they gain insights into the distribution of dark matter and its role in cosmic evolution. 3. Interactions with other superclusters. The Great Attractor's gravitational influence extends beyond the Laniakea supercluster, impacting neighboring superclusters and their dynamics. The gravitational forces exerted by the Great Attractor can interact with the mass of other nearby superclusters, creating a complex web of gravitational interactions. These interactions can lead to phenomena such as the infall of matter from one supercluster to another, altering the dynamics of both structures. The interplay between the Great Attractor and surrounding superclusters exemplifies the collaborative and competitive nature of gravitational influences in the universe. Conclusion. The Great Attractor plays a crucial role in the cosmic web, connecting it to other large-scale structures and influencing the dynamics of galaxy clusters and superclusters. As a gravitational anchor within the Laniakea supercluster, it helps shape the distribution of galaxies and facilitates the formation of new clusters. The interplay between the Great Attractor and cosmic filaments, as well as its interactions with neighboring structures, underscores the interconnectedness of the universe. Understanding the Great Attractor's role in the cosmic web is essential for unraveling the complexities of cosmic evolution and the distribution of matter in the universe. As astronomers continue to study this gravitational anomaly, they will undoubtedly uncover new insights that will enhance our understanding of the forces that govern the cosmos and the intricate relationships that define it. The Great Attractor is not merely a point of interest. It is a key player in the grand narrative of the universe, influencing the formation and behavior of cosmic structures on a vast scale. Challenges in studying the Great Attractor. The Great Attractor, a massive gravitational anomaly that influences the motion of nearby galaxies, presents a fascinating yet challenging subject for astronomers. Understanding this cosmic phenomenon requires advanced observational techniques and technologies, but several significant challenges hinder comprehensive studies. This section will explore the limitations of current technology and the issues related to obscured observations, such as dust and gas, that complicate the investigation of the Great Attractor. Limitations of current technology. While advancements in astronomy have led to remarkable discoveries, the study of the Great Attractor remains constrained by the limitations of existing technology. Several factors contribute to these challenges. 1. Resolution and sensitivity. Observing distant cosmic structures requires telescopes with both high resolution and sensitivity. Many existing telescopes struggle to distinguish between closely spaced celestial objects, particularly in crowded regions like the zone of avoidance, where the Great Attractor is located. Higher resolution is essential to accurately map the distribution of galaxies and clusters in this area. Additionally, sensitivity is crucial for detecting faint objects and emissions. The Great Attractor's influence extends to regions that may harbor less luminous galaxies or those that are obscured by dust. Current telescopes may not be sensitive enough to detect the weak signals from these distant objects, limiting our understanding of the entire mass distribution in the region. 2. Spectroscopy challenges. Spectroscopy, a technique used to analyze the light emitted or absorbed by celestial objects, is vital for studying the Great Attractor. It provides insights into the redshift of galaxies, allowing astronomers to determine their velocities and distances. However, obtaining high-quality spectra from objects located within the zone of avoidance is particularly challenging due to the interference of interstellar material. When light passes through dust and gas, it can be scattered and absorbed, leading to incomplete or distorted spectral data. This interference complicates the interpretation of redshift measurements and can result in inaccuracies regarding the motion of galaxies influenced by the Great Attractor. 3. Limited wavelength coverage. Different wavelengths of light reveal different aspects of cosmic objects. While optical telescopes have been instrumental in the study of galaxies, the Great Attractor's location necessitates observations across a broader spectrum, including infrared and radio wavelengths. However, access to cutting-edge facilities capable of capturing data across these wavelengths is limited. For instance, while the Infrared Astronomical Satellite, IRAS, and the Wide Field Infrared Survey Explorer, WISE, have provided valuable information, their respective missions also faced constraints in terms of coverage and sensitivity. The need for dedicated observatories that can operate across multiple wavelengths simultaneously remains a challenge in studying the Great Attractor comprehensively. Issues with obscured observations. One of the most significant obstacles to studying the Great Attractor is the zone of avoidance, a region obscured by the Milky Way's own galactic plane. This obscuration creates several issues that complicate observations and data collection. 1. Interstellar dust and gas. The Milky Way is filled with interstellar dust and gas, which absorb and scatter light from distant galaxies. This material can obscure our view of objects located behind it, making it difficult to observe the Great Attractor and the galaxies it influences. Interstellar dust predominantly absorbs shorter wavelengths of light, such as ultraviolet and blue light, leaving longer wavelengths, like infrared and radio, relatively unaffected. While infrared observations can penetrate dust more effectively, the complete picture of the Great Attractor's influence is still obscured due to the complex interplay of dust and gas. 2. Incomplete data. The obscuration caused by dust and gas leads to incomplete data regarding the distribution of galaxies around the Great Attractor. Many galaxies that should be observable remain hidden, resulting in an underrepresentation of the actual population of galaxies in the region. This lack of data hinders our ability to create accurate models of the Great Attractor and assess its gravitational influence effectively. Incomplete data also affects our understanding of the mass distribution near the Great Attractor. Since dark matter does not emit light, its presence is inferred from the motion of visible matter. If many galaxies are obscured, our estimates of dark matter concentration and distribution in this region will be significantly flawed. 3. Complex galactic dynamics. The Great Attractor's gravitational influence is not limited to the immediate vicinity. It can extend to galaxies situated behind the obscuring material. However, the complex dynamics involved in these interactions complicate the interpretation of observational data. As galaxies move through the gravitational field of the Great Attractor, they may exhibit peculiar motions that are challenging to analyze, particularly when obscured by dust. Moreover, the impact of the Great Attractor on galaxies located behind the zone of avoidance can lead to misinterpretations of their velocities and distances. Without a clear view of these objects, understanding their relationship with the Great Attractor becomes exceedingly difficult. Conclusion: studying the Great Attractor presents significant challenges, primarily stemming from limitations in current technology and issues related to obscured observations. The need for high-resolution, sensitive telescopes capable of multi-wavelength observations is paramount for advancing our understanding of this gravitational anomaly. Furthermore, the presence of interstellar dust and gas complicates the ability to obtain complete data regarding the galaxies influenced by the Great Attractor. As technology continues to evolve and new observational techniques are developed, astronomers will gradually overcome these challenges. Future missions, such as next-generation space telescopes and advanced ground-based observatories, hold the potential to provide clearer insights into the Great Attractor and its role within the cosmic web. By addressing these challenges, we can enhance our understanding of this fascinating region and its profound influence on the dynamics of the universe. The pursuit of knowledge about the Great Attractor is not merely an academic endeavor. It is a crucial step toward unraveling the mysteries of dark matter, cosmic evolution, and the fundamental forces that shape our universe. Future research directions. As our understanding of the universe evolves, so too does our approach to studying enigmatic phenomena like the Great Attractor. With advancements in technology and new missions on the horizon, astronomers are poised to make significant strides in unraveling the mysteries surrounding this gravitational anomaly. This section will discuss upcoming missions and technologies aimed at enhancing our observational capabilities and explore potential discoveries and their implications for cosmology and astrophysics. Upcoming missions and technologies. 1. James Webb Space Telescope, JWST. One of the most eagerly anticipated missions is the James Webb Space Telescope, JWST, which launched in December 2021. As the successor to the Hubble Space Telescope, JWST is equipped with advanced infrared capabilities that will allow it to observe distant galaxies and cosmic structures obscured by dust. Its large mirror and sensitive instruments will enable astronomers to study the Great Attractor and its surrounding regions in unprecedented detail. JWST's ability to capture high-resolution images across a broad range of infrared wavelengths will facilitate the detection of galaxies that are currently hidden within the zone of avoidance. By observing the light emitted from these galaxies, researchers will gain insights into their dynamics, mass distribution, and interactions with the Great Attractor. 2. Euclid mission. The European Space Agency's Euclid mission, scheduled for launch in 2024, aims to map the geometry of the dark universe. Euclid will utilize a visible and near-infrared camera to create a three-dimensional map of the distribution of galaxies and dark matter across the universe. This mission will provide critical data on the large-scale structure of the cosmos, including the Great Attractor. By measuring the shapes and distances of galaxies, Euclid will help refine our understanding of the gravitational forces at play in the Great Attractor region. Its findings will be instrumental in studying the clustering of galaxies and the role of dark matter in cosmic evolution. 3. Wide Field Infrared Survey Telescope, WFIRST. NASA's Wide Field Infrared Survey Telescope, WFIRST, now known as the Roman Space Telescope, is another significant mission that will contribute to the study of the Great Attractor. Slated for launch in the mid-2020s, WFIRST will focus on a broad range of astronomical questions, including the distribution of dark energy and the structure of the universe. With its wide field of view and infrared capabilities, WFIRST will conduct surveys that could reveal previously unseen galaxies and clusters in the vicinity of the Great Attractor. The data collected will enhance our understanding of the mass distribution and gravitational interactions in this region. 4. Next-generation ground-based observatories. In addition to space missions, next-generation ground-based observatories are set to revolutionize our capabilities for studying the cosmos. The Extremely Large Telescope, ELT, currently under construction in Chile, will be the world's largest optical telescope. With its powerful adaptive optics system, the ELT will achieve resolutions previously thought unattainable, allowing astronomers to study faint and distant objects affected by the Great Attractor. Ground-based observatories equipped with advanced radio arrays, such as the Square Kilometer Array, SKA, will also provide critical insights into the neutral hydrogen content of galaxies near the Great Attractor. By mapping the distribution of hydrogen, astronomers can infer the gravitational effects of dark matter and gain a deeper understanding of the dynamics in this region. Potential discoveries and their implications. As these upcoming missions and technologies come to fruition, the potential discoveries arising from their observations could have profound implications for our understanding of the universe. 1. Insights into dark matter. One of the most significant outcomes of studying the Great Attractor will be a clearer understanding of dark matter, which constitutes approximately 27% of the universe's total mass energy content. By observing the gravitational effects of the Great Attractor on nearby galaxies and clusters, researchers can refine their models of dark matter distribution and behavior. These insights could lead to breakthroughs in understanding the nature of dark matter itself. For instance, if observations reveal unexpected characteristics or distributions of dark matter, it may prompt new theories or modifications to existing models, potentially reshaping our understanding of fundamental physics. 2. Understanding cosmic evolution. The Great Attractor's influence extends beyond its immediate vicinity, affecting the formation and evolution of galaxy clusters and superclusters. Research conducted with advanced telescopes could yield valuable data on how galaxies interact and evolve under the gravitational pull of the Great Attractor. Such findings will contribute to a broader understanding of cosmic evolution, helping astronomers piece together the history of galaxy formation and the role of gravitational forces in shaping the universe. This knowledge will enhance our comprehension of large-scale structures and their development over billions of years. 3. Revealing hidden galaxies. One of the most exciting prospects of upcoming missions is the potential to reveal previously hidden galaxies within the zone of avoidance. As telescopes like JWST and WFIRST penetrate the obscuring dust, they may uncover a wealth of new galaxies that have remained undetected. These discoveries could lead to a more complete understanding of the Great Attractor's influence on galaxy populations and their distribution. By mapping these hidden galaxies, astronomers can gain insights into the complex interactions occurring in this gravitationally active region. Unraveling the cosmic web. The Great Attractor is a vital component of the cosmic web. and studying its role will provide important context for understanding the large-scale structure of the universe. As researchers gather data on the distribution of galaxies and clusters influenced by the Great Attractor, they can better understand the filaments and voids that constitute the cosmic web. This understanding will not only enhance our knowledge of the Great Attractor itself, but also contribute to a holistic view of how galaxies and clusters interact across vast distances. The interconnectedness of cosmic structures will become clearer, allowing for more accurate models of cosmic evolution. Conclusion: the future of research into the Great Attractor is bright, with upcoming missions and advanced technologies set to revolutionize our understanding of this gravitational anomaly. As telescopes like JWST, Euclid, and WFIRST come online, they will provide unprecedented insights into the dynamics of galaxies and the role of dark matter in the universe. The potential discoveries stemming from these investigations could reshape our understanding of cosmic evolution, reveal hidden galaxies, and unravel the mysteries of the cosmic web. As we advance our observational capabilities, the Great Attractor will remain a focal point for exploring the fundamental forces and structures that define our universe, paving the way for new discoveries that will deepen our understanding of the cosmos. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.